This is such a cool problem. So for this problem, I want you to kind of, first of all, try to wrap your mind around what's going on with it. We have here a plank of wood. Let it be a plank of wood. It doesn't have to be. So some kind of plank set on top of two cylinders that are free to roll. So like a way you could set this up to just kind of wrap your brain around it physically is put a book, like a hardback book, on top of maybe two markers or something, two kind of thick pens, and just put your hand on top of the book and roll, move the book back and forth such that the pens roll underneath it. And that helps you. That can help you see that the way the pens travel is going to be different from how the book travels. So that's part of what we're looking at in this problem is we're looking at how the system works together. So this is a plank on top of two solid cylinders. We're going to assume perfect rolling, so no slipping here. The rollers are solid cylinders. We're given the mass of the plank, big M, the mass of each roller is little m, radius of each roller is big R, so the rollers are identical. And then there's an applied force here that is on the plank. So that would be like the force that, of your hand moving the book or something, right? And what I'm asking for here is the acceleration of the plank and then the acceleration of the rollers. And as I said, if you if you actually build it, just again simply a book and two pens underneath there, and you move it and you look at what the pens are doing versus what the book is doing, you can see that they're not going to move together. That eventually you'll just roll that book right off of the pens, right? So kind of try to get a handle on that before you start on the problem. That will help your brain. Okay, so let's check it out. We are going to start by, of course, drawing our free body diagrams. We're going to use a force and torque approach here. So I'm interested in, notice that I'm being asked to find just the acceleration of the plank and the acceleration of the roller. So I'm asked for these translational quantities. So that tells me that for sure I need to consider the free body diagram for these things. So the first thing I'll do is kind of map that out. So I need free body diagram of the rollers, and I can just draw one free body diagram to represent each roller. The forces on each roller will be identical here. And then I need a free body diagram for the plank itself there. And then I'm going to need a torque diagram for the rollers, right? Because the rollers, they're rolling, obviously, so they're translating and they're rotating. The plank is only translating, so that's all I'm worrying about there. So this is a neat problem to sort of test yourself and see if how your force identification skills are going at this point. They should be pretty good at this point in the quarter. So if you haven't done this problem, I'd say pause the video right now and fill in these diagrams to the best of your ability and then come back in and check. All right, so if I look at the rollers, of course, I'm going to identify forces in the way that we always have here, and that is I look at what is in contact with the body. The only non-contact force we have is weight. That's it. Any other force has to be explained, verified by contact. So if I look at the roller, there's a bunch touching it. I'll start with maybe the surface beneath it that's in contact with it. Okay, so the roller is, and I'll look at this one on the left here. So I'm considering this interface here. The roller is in contact with the surface underneath it. So the surface underneath it, I know is going to be exerting a normal force upward. I feel pretty safe about that. I'm going to call that N sub R, the normal force on the roller. And then I need to ask myself, okay, now is there a frictional force at that interface? Yeah, there's going to be. This thing's rolling without slipping, right? So there has to be some kind of static friction at that interface. And then I have to ask myself, what direction is it acting in? So consider, here's where you can look at the pens and the book situation again. If you have like blocks or something, toy blocks at your house, you can build it up with that too. But really the pen in the books works just fine. Pens. I know that in order to, if I pull the plank to the right using this applied force that's shown here, that I know that the acceleration of the rollers is going to be into the page. right? The acceleration of the rollers is going to be into the page. So right now, because of that, I can put my sign convention on the torque diagram, say into the page positive. So in order for that to be into the page, that must mean that the frictional force that's exerted by this at the interface beneath it must be to the left. That'll be a force of static friction to the left. You might need to think about that a little bit more, but I'm going to kind of leave that alone. So these are the two forces that are due to the interface beneath it. Now I'm going to change colors because now I'm going to do a little bit of analysis of what else is in contact with this roller. And now I'm looking at the interface up above, right, where the roller is in contact with the plank. So what's going on there? Well, I know I have a normal force there, right? So I have a normal force. And here you have a choice. You can just write this as the normal force of the plank, say, N sub P, the roller plank interface. Um, Here's the thing, there are two rollers here. So you got to consider this in some way. So if I just leave this as normal force of the plank, what I'm going to have to remember later is that there are two of those normal forces, right? There's going to be one for each roller on the upward on the plank. So when I'm drawing the free body diagram for the plank, I can put a 2np upward on it. Or what I can do right now is I can say normal force on the plank over 2. And that's the way I'm going to handle it. You can handle it either way. You can cut this one in half, or you can double the one on the plank. It doesn't matter, but in some way you have to represent the fact that there are two of these rollers that are supporting the plank, and that is a physically different case than if only one of them was supporting the plank. Okay, so this is how I'm going to deal with it. Of course, I have weight down here. The rollers are a little m, yeah. And then also at this interface up here, there's going to be static friction. Again, if I think about my acceleration as being into the page, right? My angular acceleration, of course, is going to be into the page. Then it helps me to see that this static frictional force here, and I'm going to call this static frictional force, I'll just prime this one, that one will be to the right. Okay. That's pretty much everything that needs to go on here. My translational acceleration is going to be to the right. So I'm going to have rightward positive, and I'll just go ahead and say upward positive here. Now I'll move to the plank and discuss that. So the plank, we just talked about this whole N sub P thing. I know that I have N sub P over 2. Each roller is contributing half of that normal force. So this upward force on the plank, now I can just call N sub P, because N sub P over 2 plus N sub P over 2 exerted by each roller is going to give me N sub P upward. I obviously have the applied force that's to the right. That's given. I've got the weight of the plank. And then, okay, let's think about this. We've got the static frictional force, and that's the static frictional force that occurs at the interface between the roller and the plank. Now, that's going to be static frictional force. Let me turn back to green. I'm going to move to this roller over here to talk about it, just because we haven't used that space yet. I am talking about this interface here focused on the plank, right? So this is Fs prime. Okay, so that means that it's a third law pair to Fs prime on the rollers. On the rollers, it was clearly directed to the right. That means that on the plank, it must be directed to the left. And furthermore, I have one from each roller. So this is actually 2 Fs prime. Okay, so that's another like factor of 2 kind of thing. Again, you can put the 1/2 in the rollers diagram, you can put the 2 in the plank, it doesn't matter as long as that factor of 2 is considered in there somewhere. So that's everything. Again, this 2 Fs prime on the plank is that could be probably the least intuitive of all these forces as far as what direction they have to go in. If you find yourself in that situation, go to the interactive object. So in this case, that would be the rollers, and just look for the third law pair. Sometimes that can help direct you if you're considering what your third law pair is going to be. Okay, and the plank, again, will be accelerating to the right, so I'll say rightward positive, upward positive. And now I'm going to look at the rollers. So the rollers, it's fairly straightforward here. I'll try to stick with my same colors for just a minute here. This is going to be my F sub S. This is R. Those are at 90 degrees apart, of course. And then the rollers also has a force on it that causes a torque on the top of the roller, right? So that's going to be, and I can look at the roller free body diagram. This is going to be what I'm calling FS prime there. And this is same magnitude R, but it's a different vector. So you could like prime this one if you wanted to be super good about notation there. But it's okay to leave the magnitudes the same if you're showing the direction with an arrow. It also shows that there's an essential difference between the two vector quantities. All right, and I have into the page as positive. Super. So now I'm ready to kind of use my equations or use my diagrams here to generate equations. Remember, these are analytical diagrams, and we don't use them just like for anything extra. We use them to generate our equations. If you're generating equations without your free body diagrams, then you're not solving the problem. Okay, so the diagrams are the heart of what we're doing. So I'm going to go ahead and apply Newton's second law to rollers. I only need to really look at this in the X. Oh, I guess I'm going to need to look at this in the Y. No, never mind too, because I'm going to need the I'm going to need to figure out what my frictional forces are. But right now I'll just look at X equations. So I've got Fs prime minus F sub S is equal to M A sub R. Now I need to put a subscript on the roller equation here, right? Because the acceleration of the rollers is going to be different from that of the plank. They're not moving together. And I think I'll go ahead and do my Y equation while I'm right here staring at this free body diagram. So normal force R is equal to 1/2 of normal force P plus mg. There's no acceleration in the Y, so those forces are equal and opposite. Okay, so Planck, I'm going to do horizontal first, applied force, minus 2 Fs prime equals big M. Now I'm going to call that A sub P for the acceleration of the Planck. That's another quantity I'm being asked for. And N sub P is simply equal to the weight of the Planck. That's a fairly simple situation. There are no other vertical forces, and the system is not accelerating in the vertical. Okay, now I can look at my rollers and generate some equations there. If I look at my rollers, I can see that I can define my two torques, right? And I see that both those torques, by now we should be pretty handy with figuring our torques out. Both those torques are going to be into the page, right? I'll take a moment and just crank those out. So torque 1 is going to be RFS, that's into the page. Torque 2 is going to be RFS prime, and that's also into the page. So this is a case where these two torques work in concert, right? They both work in the same direction, both into the page. So for my second law statement, it's going to be fairly simple. RFS plus Fs prime equals I alpha. And in this case, I can say where alpha equals A sub R over R, right? It's the acceleration of the rollers divided by the radius of the rollers. And the I value, we're told these are solid cylinders, is 1/2 M r squared. So what that gives me then, once I make all those little substitutions and do my algebra, then I get fs plus fs prime is equal to 1/2 m a sub r. So that's another useful equation that I get from doing my torque analysis there. Okay, so we have our equations. I think that is most of what we need. We just need to do a little more conceptual analysis here, and that is a really cool part of this problem. That is the part where we need to relate the acceleration of the plank and the acceleration of the rollers. So think about this. You know that these two things are related, right? You know they're related. You can play around with your book and pen setup or whatever, and maybe it's obvious to you how they are. In my experience teaching students, it's never like super obvious right when we first look at it. But I do want you to think about something here. Think about when you were learning about rolling, right? For a rolling object, let me just draw a little diagram here for a little bit smaller. For a rolling object, remember that the very bottom where the, like say this is a wheel or something, a car, I don't know, but for something that's rolling, the very bottom where it's in contact with the substrate underneath it, like let this be a rolling wheel. That just brings it into language that we kind of know, right? And the car or bike or whatever is going that way. So we know that where the tire is in contact with the ground, there, the velocity at the bottom is equal to 0. That contact patch is at rest with respect to the ground. That's why it can drive the car forward. You might need to spend time with that if you haven't already. Here's the velocity of the center of mass. That's just whatever the car's speed is, right? So the velocity at the center of mass here is whatever the car's speed. So this would be like, I'll call that V prime, and this is just the car's speed, whatever your speedometer says. That's the velocity of the center mass of the wheel, the middle. The top of the wheel, you might remember, is actually going twice as fast as that. So this is 2v prime. So the top of the wheel is actually going twice as fast. And a way that you can kind of think about understanding this is, if you haven't thought through this yet, is consider the wheel to be an object that's rotating about, and instead of considering the axis to be at the middle of the wheel, what if you consider the axis to be at the point of contact with the road? Yeah? If you do that, then it allows you to see that actually, if you conceive of it that way, right, just for a moment to wrap your head around it, then the radius is actually measured out this way from this contact point with the road. And you can see that the farther you get out on radius, of course, the greater the tangential speed is going to be. That's something that you already knew. So that kind of helps you wrap your mind around how at the very top of the wheel, the actual translational speed at the top of the wheel is double the translational speed of the center of mass. So if the car is going 50 miles an hour, the top of the wheel is going 100 miles an hour. Okay. This is one of the reasons that, like, I don't know, say a gravel truck or something is driving and a piece of gravel falls on the top of the wheel of the truck as it's flying down the highway. That piece of gravel gets launched at like 120 miles an hour, right? Or more, and can break windshields and do all kinds of damage. So that speed is really, really fast. It's much faster than if it was just like falling off the truck itself. So that's usually the cause for windshields getting shattered by objects that are thrown around on the road. Okay, so that's where I'm going to kind of leave this for you now. This is a really fun problem to kind of chew on, but this what we just talked about up here helps you figure out how to come up with that relationship between the acceleration of the plank and the acceleration of the rollers. And all the details are in the written solutions, but I think that's worth you spending some time thinking about on your own.